Oops, sorry. All right, so Ms. Shapiro is here again, and we're going to talk a little bit about energy transfer in ecosystems. It's video number 2, so I look the same. Enjoy. Um, so this is, I'm not sure what number this is on the CED, but maybe 2.3. No, that doesn't sound right. Towards the end. So what happens to the energy in an ecosystem? We know that all of the energy in the ecosystem is begins with the sun. A few ecosystems, such as those at the bottom of the ocean, begin with deep sea thermal vents that have sulfur coming up. And then those autotrophs, producers, plants, are able to convert that energy into chemical energy. And much of that energy is lost. Plants are very inefficient. They absorb something like 10% of the light from the sun, and the rest of it is reflected and not absorbed. But plants, or autotrophs, things that make their own food, are able to absorb that energy and they turn it into chemical energy. Remember, the first law of thermodynamics tells us that energy is neither created or destroyed, it's only transferred. So they transfer that light energy into chemical energy, and then those plants get eaten, and the primary consumers are able to convert the chemical energy that's in the plant into energy for themselves. Remember that they eat, so they're the heterotrophs. Either way, only 10% is transferred, and we symbolize that with the arrow. So the arrow shows how the energy flows. And 90% of that is lost as heat. And that abides by the second law of thermodynamics, which tells us that the entropy of the universe must increase. We could think of entropy as disorderedness. And so every time we have heat increasing, we have disorderedness increasing. And so that's kind of how our first and second laws of thermodynamics relate to this. So again, plants are able to take it, they're going to perform photosynthesis, they're going to take it from the light, that light energy, and they're going to convert it into chemical energy, and much of it is lost as heat. And then the same thing, the primary consumers get eaten by the secondary consumers get eaten by the tertiary consumers. There's not really more than 4 levels in our ecosystems usually, just because there's not enough energy. And so we'll see that our energy pyramids are these classic pyramids because the energy is degraded and that it's lost. The ocean can have a little bit of a bigger ecosystem just because the ocean is so large. And so here's just a really great picture of this. We see that our pyramid of energies are always that classic triangle shape. And here you can see the amount of energy. This is probably in kilocalories, how much is really available for tertiary consumers. That's why we don't have larger amounts, because there's just not enough energy in the ecosystem. But again, you see that transfer between the different levels, the producers or the autotrophs that are making the food, primary consumers, secondary, and then tertiary. Overall, all of the energy that a plant makes is called its gross primary productivity, and we measure it in kilocalories per meter squared per year. So this is how well does the plant, or how much energy does the plant convert from sunlight into actual energy. Now, plants do things. They create flowers, they respire. That means that they're going to also take in oxygen and make energy. They have an immune response, they have to make new leaves. So not all of the energy that they make is available in the tissue. Some of it is lost as heat, and some of it is used for other things, such as like an immune response. And so the rate at which the ecosystem's producers convert solar energy minus the rate at which they utilize that energy for themselves, that respiration, so they need energy for their own bodies. So however much energy they use is subtracted out from how much they make. And so we're left with the formula NPP is equal to GPP minus R. And it's not written here. Oh, I guess I can probably hold, please. Annotate. So now I'm going to write, right? We have this formula, and our formula is NPP, ooh, you can't see my face anymore, equals GPP minus R, and that stands for respiration. Okay. Ultimately, NPP is what drives the number of consumers that we have. If NPP is very low, then we won't see a lot of producers, we won't see a lot of consumers. Let's see what else. So on this graphic, we see all of the NPPs for different ecosystems. You can see that swamps and marshes have the highest NPP. They have tons of plants, tons of producers. Tropical rainforest is next, then other forests such as temperate forests, the taiga, the savanna, and then agricultural land. Notice how far down our agricultural land is. So that means that we're making our food that we eat for energy in an area that's not very productive. You see that desert scrub is down at the bottom, and deserts are almost minimal. If we look at aquatic ecosystems, we see that estuaries, remember that an estuary is a place along the coast where salt water and fresh water are going to combine. We see that they have the highest NPP, and that's the wetlands are very, very, very productive. We see that the open ocean is not very productive, but it does produce a lot of oxygen, and it produces high NPP when we consider its total area. So for example, this is net, this is the average, and so the open ocean is relatively low. But if we consider that 75% of our world is covered in the ocean, they actually have really high productivity. The other thing that we might want to consider is not NPP and GPP, but what happens to these organisms that are here on the screen, the consumers. And so those are what we refer to as our secondary production. And so I'm going to type because it's a little bit neater, okay? And so what we see that consumers are what we call gross secondary productivity. And it's the same thing. It's how much energy do we see in these particular organisms or this particular tropic level. And we have the same formula that the net secondary productivity is equal to the gross secondary productivity minus the respiration rate. But in this time, we can calculate the respiration rate. It's equal to the amount of food that an organism takes in minus the amount of fecal loss or the poop. And so what we see is that the amount of energy available in a tropic level for consumers at the primary consumer, secondary consumer, it doesn't really matter, is that NSP equals GSP minus R. All right, I think that's mostly what I have here. Let me just double check as we move through this PowerPoint. I think that's it. That's all I got. So I hope that this was helpful. If you have more questions, let me know. Thank you.